So we left off on this example. This is now part 2. I want to show you some things that were in the textbook. These are several pages of common geometric linear transformations. We're going to always ask ourselves, where does E1 go, and then where does E2 go? So when you reflect through the x1 axis, so you have a flip from the first quadrant into the fourth quadrant, for instance, E1 just stays the same. 1, 0 just stays 1, 0. However, 0, this should be a 0, 1. Excuse me there. This should be a 0, 1 right there. That would flip onto 0, negative 1. So change that to 0, 1. 0, 1 flips to 0, negative 1. So that's the transformation shown here of what's typically 0, 1. Whereas 1, 0 stays the same. Remember, E1 is 1, 0, and E2 is 0, 1. T of E2 is 0, negative 1. What would it be if it was a reflection across the y-axis or across the x2 axis? Well, the 0, 1 now stays the same right there, whereas 1, 0 now becomes negative 1, 0. And there it is. Always ask yourself, what happens to E1 and E2? And this becomes the new A matrix, the transformation matrix. Some more common reflections are reflecting over the line y equals x. So here, 1, 0 would flip over to here and become 0, 1. So typically this is 1, 0. It's now transformed into 0, 1. The vector 0, 1, that unit vector becomes E1, becomes 1, 0. This is your new matrix. If you reflect over the line y is negative x, or x2 is negative x1, you'll see these transformations. 1, 0, where does 1, 0 go? It goes to 0, negative 1. And where does 0, 1 go to? It goes to negative 1, 0. If you reflect through the origin, this ray in the first quadrant would go to this ray in the third quadrant. E1, reflecting over the origin, you can think about it as turning it 180 degrees, it would go over here to negative 1, 0. And E2 would flip 180 degrees and go to 0, negative 1. Some more transformations are contractions or expansions. In this contraction, E1 goes to, instead of 1, 0, goes to K0. E1 is going to K0. Did E2 change at all? Nope. E2 stays the same as 0, 1, only E1 changes. Versus if it's a vertical contraction, here E1 stays the same, but E2 is either expanded or contracted. And instead of 0, 1, you stop at 0K. So this would be the A matrix that you could use to find any transformation of any x. So the shears are also really fun. E1 in this case, notice, stays the same. E1 doesn't change. E1 is the same on the blue as it is here in the black. However, E2 started as 0, 1, and where does it go? Whoosh. It goes over here to K1. It's just going across. So the height is still the same. It's just being sheared to the left. There's a picture of a sheep in the book. I don't know what that's about, except you shear a sheep. Who knows? Anyway, over here, notice that E2 stays the same, but E1 is sheared down. Instead of 1, 0, it's at 1K. Now, if you project onto this axis, okay, E1 stays the same. E1's already on the x1 axis. However, E2 goes down to 0, 0. And here, if you project onto the y-axis or the x2 axis, notice E2 stays the same, but E1, all of E1 goes to the axis. So the x and the y components are 0. Nope, I didn't mean it like that. Everything goes to 0. So where does 1, 0 go? 1, 0 goes to 0, 0. That's all you're asking. Where does E1 go? E1, which is normally 1, 0, goes to 0, 0. Okay, so we're going to get into onto and one-to-one. Let's start it on this video. Go about 5 more minutes here, and then I'll see where I am, and maybe we'll do a third video. Okay, so transformation Rn, so this is the space where the domain resides, and Rm is the space where the codomain is. So a transformation is onto if every single vector B in the codomain is the image of at least one vector x in the domain under that transformation T. So if you have AX equals B, that means there's at least one solution X for every single B. So here, notice this B is an image. It came from a preimage. AX would equal that B. This other X would equal this other B. This other X equals this other B. However, this poor B is in the codomain, but it has no preimage. That means this function is not one-to-one. I'm sorry, it is not onto. Not onto. Now, if I get rid of this guy, now we have a onto relation. So you're always going to ask yourself, is B in the range? If the answer is yes, then you know that AX equals B, and that image has at least one preimage. So is B in the range? This answer will always be yes if the columns of A span the codomain. If the columns of A span the codomain, that means that every single row has a pivot. We'll talk more about that in a minute. The linear transformation from R2 to R2, for example, rotating vectors counterclockwise, that is onto. How do we know that's onto? Well, for every vector in two-dimensional space, you can find a preimage. So if I rotated a vector 90 degrees counterclockwise, then did it come from somewhere? Yeah, it came from a vector that if you rotated 90 degrees clockwise, that's the one that it came from. So every single vector in R2, you can say, yes, this came from another vector that was rotated 90 degrees. In fact, you could even say what that vector is. However, this one that we did with the 1/2, remember that guy? We started here. I'm on number 13. Okay, so if I would go back to number 6, this one with the 1/2 that projects onto the line, y equals x, we did that in the last video. That transformation matrix right here is A. So what happens with that is that one onto. In other words, if you take A times any x, can you generate every single B that's in the codomain of R2? Well, this B is in the codomain of R2. Does x exist? Well, take a look. Here's A, and then you multiply by whatever x. Can you ever equal 3, 1? Well, no way, because you have 1/2 x1 plus 1/2 x2 is 3, but you also have 1/2 x1 plus 1/2 x2 is 1. Does not work. So B, this particular B is not in the range of AX equals B. However, 3, 1 is in the codomain. This is not an onto transformation. If the range is equivalent to the codomain, then T is onto. Let's look at one-to-one. A transformation T from Rn to Rm, domain to codomain, is said to be one-to-one. You can also do this symbol, 1-1. if each vector B in the codomain is the image of at most one vector x in the domain under this transformation. Okay, so this would be the bijection here. If B has one and only one preimage, T is one-to-one and onto. Think about if a function passes the horizontal line test, it's one-to-one. And in order to be a function, it already passed the vertical line test. However, this one would not be onto because y is -1, has no preimage. So let's look at linear transformations. So the linear transformation rotating vectors counterclockwise is one-to-one because every single image has at most one preimage. There's not two different vectors that you rotate 90 degrees counterclockwise and they end up being at the same place. This one is not one-to-one. Why not? Well, you want to know, is B unique? Is X unique for every B? So the B ones for this have to be the same for the X and the two numbers. So either both 3, both 1. So here, if I took 2, 0 as my input, I would do AX equals B and get that B. However, that input is not unique because AX, when X is 0, 2, AX is also that same 1, 1. So it's not one-to-one since X is not unique. So note the columns are not linearly independent. Therefore, we are not going to have a one-to-one relationship. Okay, I'm going to stop there and then we'll come back and just look at the summary and that'll be quick. Okay.